It's my privilege to introduce Ms. Gunja Malik, IBM Quantum Ambassador and Senior Technical Staff Member at IBM Cloud India. With a long industry experience, Ms. Malik has been associated with IBM in various senior technical and leadership roles. She has played a pioneering role in advancing IBM's cloud and quantum initiatives and has mentored several teams in adopting quantum computing approaches. She is also actively involved in IBM's global outreach programs to create awareness about quantum technologies in academia as well as industry. Today, she will be speaking on quantum computers and machine learning. Her experience in bridging practical cloud computing with quantum innovations makes her lecture an invaluable learning opportunity for all participants. Welcome, Gunja Malik.
I'm sorry, I was speaking on mute. Thank you, sir. Would you like me to wait for another 2 minutes while people join?
Sure.
Okay. Okay, hopefully everyone is able to see my screen now.
Yes,
Yes,
ma'am.
madam. Yes, madam.
Okay. All right, thank you. Hello, everyone. Thank you for giving me the platform to speak about quantum machine learning. I'm Gunja Malik. As I introduced, I'm a security architect in IBM Cloud, and have been pursuing quantum computing as an interest for the last 5 years. I'm also an IBM Quantum Ambassador and have been really enabling the students and the faculty on quantum computing for quite a few years now. Today's topic is quantum machine learning. So this is the agenda that we will follow. In summary, we are going to look at machine learning preliminaries to begin with. Before we get into the realms of quantum computing or quantum machine learning, it is important to understand how can we really encode the data onto these quantum devices. And then we will take a look at specific quantum machine learning algorithms like the quantum kernels and support vector machines. And then we will also take a look at the variational circuits and quantum neural networks. Let's get started with the machine learning preliminaries itself. This is a very basic definition of what machine learning is. It is nothing but a collection of machine learning algorithms which is used to understand, learn the data patterns and the relation between that data features such that it can derive certain inferences from that data and give predictions or outcomes which can be utilized for certain tasks that we want to achieve, we want the model to achieve. And for this particular aspect, the machine learning itself will learn certain parameters without being given explicit instructions on how to learn those parameters, and then define a model which is more generalized, which can then also predict outcomes for the data it has not learned. In short, what we are really trying to achieve is something that will help humans perform a task better without going through enormous amount of data that is currently available, and perform tasks efficiently. It has applications into various areas. You are aware of the natural language processing, which is seen in the LLM models that is currently being used as ChatGPT or Gemini, etc. But it also has applications in the recommendation systems, which comes in various domains. For example, the medical diagnosis, or the finance predictions, or even the autonomous vehicles. Image recognition is another area where it is extensively used, and it has variety other applications as well. Now that we understand what machine learning is, let's look at the mathematical aspect of it. So machine learning problem can be defined as a function approximation and optimization problem, where we look at a specific data set, which has a true function, let's say g of x, where x is the data features that we have. And we approximate another function f of x hat with a parameter theta, such that we can then define a mathematical model which approximates this particular data set. Now, in this particular image that I have shown, I have a flower image, and the data features can be considered as the different pixel values of this particular image. All these pixel values can be considered as data features, which can be fed into the function f of x theta, x hat theta, to determine the hypothesis function, which will classify this as a true image, which has a flower or does not have a flower. The objective of this function is really to learn the hypothesis, to define the hypothesis, and learn the parameters, which will give an approximate function or mathematical model, which will help us to classify any other image which it has not even seen before into an image which has a flower or it does not have a flower. And that is what the entire objective of this particular mathematical model would be. Machine learning algorithms can be categorized broadly into three different types. The first is the supervised learning, which has two different type of algorithms where classification or a regression problem can be solved. These supervised learnings, as the term indicates, is looking at the labeled data within the data set, which helps it to classify or associate the regression values correctly. If the problem is, or the outcome of the model is really classifying the objects into different classes, it is called a classification problem. If instead of classifying, it is generating a continuous value in a continuous interval, that is a regression problem. This is taking example of the example that we have already seen. If I'm classifying an image as a image which has a flower or does not have a flower, that is what a supervised learning classification algorithm can perform. Another type of algorithm is the unsupervised learning algorithm, and we have different types of algorithms within this. In the unsupervised learning, we do not provide any labeled data in the data set. So what the algorithms really do is look at the training data and learn the different patterns and the structure within the data to determine what are the optimum values or parameters that will help the model look at the unseen data and determine the predictions. In this case, we have the dimensionality reduction algorithms, we have the clustering algorithms, and we also have some generator models like the generative adversarial networks or the variational autoencoders, which enable the model to predict or to generate certain similar text as it has been trained upon. So this helps us to generate samples or synthetic data that can be used for further training the models. Then we have the third category where the reinforcement learning is done. And in this category, the agent itself is not trained on any data. Rather, this agent learns by interacting with the environment it is currently in. Based on the actions that the agent performs and the reward or penalties that the agent gets, it defines its strategy and a policy based on which the future actions are taken. Over a period of time, this agent's goal is to accumulate the maximum cumulative rewards over multiple iterations, and that is how it will continue to define its policy and ensure a good outcome for the objective it is defined for. Here is a simple generic workflow of supervised learning, where first we have a training data set, which is called the X-train here. Along with the training data set, of course, we have the labeled data as well, which is the Y values associated with this X-train data set that we have. This is a tuple that is fed into the model. The model here is the f of x train and theta, which is responsible for generating the predictions as y hat. The idea here is to take the value of y hat and see how close it is to the label data set that we have provided, which is the y. The difference between the two is going to enable us to get the cost function. Here we have used the mean square error metric, which is used as the cost function. Here we take the difference between the actual label and the predicted value, and we sum all these values across the samples that have been used for training the model and divided by the number of samples in the training data. This helps us to determine how close the predicted value is to the actual value. Now, in order to make sure that we are minimizing this cost function, we take a gradient of this cost function and learn the delta parameter value update that we need to make and update the model parameters so that in the next iteration, the updated parameters are used and the values are determined the outcomes are determined based on the updated parameters. Now, these iterations continue for multiple such cycles, such that when the model generates a result which is optimum, I wouldn't say completely accurate because we want to have some generalization in the model as well. So when it reaches an optimum learning and is generalized well, this model is then fed in the unseen data to predict the outcomes, which is fairly close to what the outcome should be. So in order to come to a point where we define whether the model has been generalized well, this is a plot of the metric, the error function, against the complexity of the model. Here we can see that it is the trade-off between the variance and the bias that will enable us to determine when do we really stop the training of the model and start using it for actual predictions. On the left side is the underfitting regime, where you will see that we have the high bias and the low variance, which essentially means that our model is too simple or it has not been trained with enough data to understand the different data patterns or structures and cannot do a good prediction for the unseen data as well. On the other hand, the right side is the overfitting regime where the bias is low, the variance is high, and it essentially means that our model has learned the training data so well that if fed an unseen data, it will not be able to perform good predictions. So what we really need to do is come to a trade-off where our variance and bias are at an optimum level and our predictions are well, whereas our training also has not been completely done, so that we have minimal generalization error, and we can say that our model is now generalized well to start predicting for the unseen data as well. Before we start looking at quantum machine learning, we first need to understand, why do we even need to do quantum machine learning? We already have quite a few classical machine learning algorithms which are running efficiently and are actually predicting the outcomes. So why do we have the need for learning quantum machine learning? So when we look at, if we consider the era we are in today, this is the era of utility, where we have error correction mechanisms and error mitigation mechanisms. I wouldn't say error correction, but error mitigation mechanisms well defined, which enable us to run certain algorithms on these quantum computing devices we have today. Also, with the evolvement of the number of qubits in these devices, it's much easier now for us to look at certain practical problems that were intractable on classical computers and try to solve them on quantum devices. But before we do that, it is important for us to understand that today, if we solve a classically intractable problem on a quantum device, there are high chances that subsequently the same problem can be solved on, someone will come up with a solution that the same problem can be solved on a classical computer. And this iteration will go on till a point where the two computing devices stretch the limit of each other. And at a point, the quantum devices will be able to solve certain problems which the classical computation devices will not be able to solve. And at that point, we will really come to a quantum advantage and see how those algorithms then can be used to solve some practical problems which the classical computers will not be able to do. But with that said, if we look at a particular training data set, for example, in this case, we have a two-feature data set, which is really a classification problem where we want to classify the data set into two different categories. Now, this is very simple to do because even if I look at it with my eyes, I can differentiate that there can be a linear line, there can be a line which separates the two data sets, and it's a very easy problem to solve even using a classical computer. We have now, while that could be done by using a supervised learning, we have unsupervised learning as well, where the data model can learn the data patterns and then automatically define that there are different clusters in which a particular data set can be divided. Now let's take a look at this data. Now here we have a mixed data of two different classes, but it is really difficult for us to classify it into different classes using a linear boundary. Now, in order to solve this problem, if we take this particular data to a higher dimension, now we will see that it's much easier to create a linear plane boundary which divides the two data sets. Now, when we think about any data where we need to go to a higher dimension, we should automatically think of quantum computing and see if that is where, if we can solve this particular problem well, if we bring in the quantum device and perform the quantum machine learning. To understand why that is the case, let's understand the difference between the classical computation and the quantum computation. Now, when we talk about classical devices, classical computing devices, we are talking about classical bits, which is 0 and 1. These are the two possible states with a bit string having any one value at a particular time. But when we talk about quantum bits, this is where we can have the value of 0 or 1, or we can actually have the two values simultaneously as well. So if we expand this to a 2-qubit system, we clearly see that a 2-qubit system can have 4 states versus a 2-bit string having any one of the values of the 4 strings. A 4-qubit system can have 16 states simultaneously, which helps us to perform computation at a scale, whereas a 4-bit string can have only one of the 16 states that is possible to have using a 4-bit string. Now, scale this up to a 20-qubit machine or a 127-qubit machine. You can clearly see the advantage we can bring in if we perform the computation on a quantum device. Now, if we look at the differences between the classical bit and the quantum bit, it is important to understand that these quantum states have a complex amplitude as well, while the classical bits are purely real values. The qubits can have unitary operations performed in order to manipulate the quantum states. And these quantum devices are subject to different types of noise. What it essentially means is there are multiple such differences between how a bit can be manipulated versus how a qubit can be manipulated. And that helps us to identify certain algorithms that can run well on quantum devices, while the same computation cannot be performed well on a classical device. And that is where it is important to identify what are those use cases and what are those learning, or what are those algorithms which can be performed well on a quantum device and can really manipulate the quantum states in high dimensions, which are difficult to solve using classical computers. The two things that are very clear from what we discussed so far is that machine learning really performs manipulations in very high dimensions. And what I showed you was a 3-dimension problem. But then if you look at the data today, it spans across multiple thousands and millions of such dimensions. And so it is really important to understand whether the particular problem that we are solving would be much easier solved on quantum computations, quantum computers with which can manipulate data in high dimensions very easily as compared to the classical computers. Now, when you think about quantum machine learning, it is important to clear the notions of what is quantum machine learning versus the classical machine learning that we have today. If you search about it on the internet, you will come across this 2x2 matrix where the definition of using a classical data with the classical algorithm is the classical quantum machine learning part, and the QQ here is the regime where we have the quantum data used with the quantum machine learning algorithm itself. What we are going to focus as part of the quantum machine learning is the CQ regime, where we are looking at the classical data set and we are performing quantum machine learning on the classical data set. That is what we are going to focus on. When I say quantum data, what it really means is that we already have a circuit which is giving us a quantum state or quantum data on which we are running the quantum machine learning algorithms again. But we are not really going to look at that data set right now. What we are going to do is we are going to take the classical data, encode it into a quantum state, and then perform the quantum machine learning. Now, on the right, we have the generic supervised learning workflow that we had seen earlier. And we will just be using this classical data here. And this model would essentially be our quantum machine learning model, and rest of the components would remain the same. It is also important to call out that with the noisy quantum devices that we have today, even though the error mitigation techniques are being implemented, there are only certain near-term algorithms can be executed on the near-term devices. Certain algorithms can be run on the near-term devices, and those would be the quantum support vector machines and the quantum neural networks. We also have certain algorithms which can only be run on the fault-tolerant quantum devices, which is not going to be the scope of our discussion today. Those algorithms are HHL algorithm or the quantum principal component analysis. But today we will focus on more near-term solutions that can be implemented on the devices we have. On these slides, we also have certain papers which you may want to go through to understand more on the specific studies that have been performed on the quantum machine learning algorithms. Now, before we get into the details of how the quantum machine learning algorithm can be implemented, it is important to understand how do we really encode the classical data onto these quantum devices. Now, the reason why I'm saying encode is because we are actually manipulating this particular data set into a state or into a mapping capability on the qubit, such that we can perform manipulations or unitary operations on those quantum states. It is not a one-to-one exact value of what the classical bit might be. Let's look at some of these examples to understand this better. Now, first encoding here is the basis encoding. Let's take this as an example, which is a 2x2 pixel image. Here, the values in these pixels are the value of the pixels themselves, which will act as data features for our examples. This is one single sample data that we are talking about. So if you have to think about multiple such samples, you will just need to extrapolate the number of qubits required in order to understand how many qubits might be required, or how those qubits would need to be simulated or mapped to the quantum states themselves in order to perform the computations. Now, taking examples here of this 2x2 pixel data or image, in order to encode this onto a qubit, I would flatten this particular data set to generate a feature or a data vector as is called out here. So here is my data vector, which is 3103, which essentially represents this pixelated image. Now, first I will convert this particular value into a binary string, which is what you can see here. In order to encode this particular value onto the basis of the qubit itself, I will need two specific qubits. Because it's a 2-bit string, I would need 2 qubits to now encode this particular value of 3 onto the 2 qubits as a basis encoding. So if I have to now encode all these 4 data features, you can easily see that I would require 8 qubits to encode all these 4 features onto the qubits. So on a computational basis, if I want to encode 0, 1, I will have 2 qubits prepared in the 0 state, and I will perform the X operation on my second qubit in order to get the state of 0, 1. Now, if we look at the advantage of this particular encoding, it's very simple to understand. I can easily see that I have a data feature 3, and I have the basis encoding 3 here, which is 1, 1 here, which is very easy for me to understand. However, the challenge here is that, as I had mentioned, if I entangle the qubits, these entangled qubits can have multiple states at the same time. But instead of using all the available states, I'm using a 2-qubit system only to represent one string here, which makes the data vector very sparse and does not make this a very efficient mechanism or technique to implement the encoding. The second is the amplitude encoding. Now, again, we'll stick to the same data feature that we talked about initially. Now, in order to apply this onto the amplitude of the qubit itself, it is important that we implement the natural quantum normalization that is required. And hence, you can see that first we will have to normalize this data and then encode it to the amplitude of the different qubit states that I have for this 2-qubit system. Now, it is quite easy to understand. We have these 2 qubits. We apply the unitary operation to actually apply these states to the amplitudes of the qubit itself. Now, this is a block sphere, which is a 2-qubit system, which I have prepared, and I have entangled and prepared. Now, if I have to apply the amplitudes to this 2-qubit system, I would apply these different states to the different states that are available. And so you can see that now we have different amplitudes applied to the 0, 0 state, the 0, 1 state, 1, 0, and 1, 1 states, based on the unitary operation that I have performed onto these amplitudes. Now, this essentially means that all my amplitudes reside within the Hamiltonian and gives me a data set on just 2 qubits. As can be seen, the advantage here is that I am able to now encode my data feature into a fewer set of qubits, and it requires only log 2n qubits for the encoding. But the disadvantage is that now any algorithm that is going to perform computations on these qubits needs to operate on the amplitudes of the quantum states, which becomes very inefficient. not only from the state preparation perspective, but also from the manipulation perspective. Next is the angle encoding. Now, what we have seen so far is the basis encoding and the amplitude encoding. But here, instead of looking at the amplitude itself, now let's take a look at the angle of the qubit itself. So angle is when we are moving away from the z-axis. In the zero state, we will have the qubit aligned with the z-axis. If we move away from the z-axis, that is when we have the angle theta, and encoding these data features into this angle gives us the data encoding. Now, this encoding can be performed either by rotating around the x-axis or around the y-axis. But it should be noted that if I rotate it around the x-axis, my qubit would then have a complex component added to it. And hence, in the literature, you would generally see that the rotations are performed along the y-axis, which gives me all real values. So in this encoding, we have for a 4-feature data set, I would want to have 4 different qubits, where each qubit will have the data encoded for one particular data feature. And so the system will be a tensor product of the equation provided here. So what I'm really doing is applying this theta value in which I'm encoding this particular single data feature. So I have 4 different qubits prepared in the zero state, and I'm performing the Y rotation on each of these qubits such that I'm able to encode this particular value into the qubit. Now, it is important to understand that when we are talking about angle encoding, we have rotations from 0 to 2 pi. So in order to make sure that we are really not losing any information because of the rotations going past the 2 pi, it is important that we scale the data before it is applied so that we don't end up losing any information in the process. The advantage here in angle encoding, as you may have realized, we have only one layer constant depth for performing this encoding. We have just one unitary gate that is applied to each qubit, and that makes the entire encoding very efficient to implement. The disadvantage here is, as you can see, we are using n qubits for n data features as against what we could have done if we use the amplitude encoding. Next is the phase encoding. Now, in case of phase encoding, instead of looking at the theta, we are looking at the value of the phase here, and we are really encoding the data into this phase. So here, first, I have to set my qubit into the superposition state and align it with the plus x-axis. This can be done using the Hadamard gate, and then I apply the phase to this particular qubit so that I can encode the data here. Again, in case of phase encoding, as you may appreciate, the values can be only between 0 to 2 pi. And hence, again, it is important that I scale my data well such that I do not end up losing information when I start encoding this into the phase of the qubits. So here, as a circuit, I have my states prepared in the zero state. I apply Hadamard gate to each of these qubits to bring them into superposition state and align it with the plus x-axis. And then I apply the Z rotation on each of these qubits to apply the required phase so that my data gets encoded. The advantage here is, although it is the depth is more than the angle encoding, but it's still a constant depth of 2, and it's quite efficient to implement. The disadvantage again here is that we have n qubits that are required for the data encoding. Now, we can always come up with more efficient ways of encoding, techniques of encoding. And here is one such technique, which will give you a sense of how we can combine different techniques to implement much more efficient encoding schemes. Here, we are going to look at the combination of the angle and the phase encoding. Using the same data set feature that we have taken in the previous examples, my qubit is aligned with the zero state here. Now, first, I will encode my first feature by applying the angle encoding that is rotating around the y-axis. And then I can apply my phase encoding by rotating it around the y-axis. And that means now I have two different features that I have encoded on the same qubit. So here you can see the tensor product of the two qubit system, because I will require two qubits to perform the encoding of these four features. And you can see that a phase component is introduced here in the formula. Now, when I want to build the circuit, of course, I have my two qubits, which are initialized in the 0 state. I apply my Y rotation to encode the first set of features. So now I have two features already encoded on these two qubits. And then I perform the Z rotation to additionally encode my two other features on the same set of qubits. And now it is clearly an advantageous encoding technique where I have half the number of qubits that are now used for encoding the data features. Sorry, is there a question that anyone had? Okay, all right. So then let's proceed to the next set where we want to look at how the encoding can be. Sorry, does anyone have a question? I'm hearing some noise.
Yes.
Yeah, please tell me. Would you like to ask your question, please?
Hello.
Yes.
Am I audible? Ma'am, my question is how to decide which encoding technique is applied to particular data?
And that is a very good question. So there is no specific formula or defined yet when you should be applying which encoding. The idea of giving you information about the different encoding techniques is to give you an intuition how data encoding can be performed and how you can efficiently encode certain data features. But based on the kind of problem you have and the data set you have, it will be important for you to really play around and identify which encoding mechanism might be better for you to use for your data set and for the specific problem you're trying to solve. It will depend on the algorithm, it will depend upon the data set, and these are not the only encoding techniques. Rather, you can also try and build your own techniques and identify a more efficient one which will work well for your problem.
Okay, thank you so much.
All right. Okay. So now let's take a look at encoding at arbitrary points. And what I'm essentially trying to do is, I had my combination of angle encoding and phase encoding, which enabled me to now use fewer qubits to encode the features. But can I make this more dense? When I say make it more dense, is can I use the same qubits for encoding more features and make it more efficient for my problem statement. So here now in the first diagram here, I'm encoding 8 features on 2 qubits. Let me explain this a bit. What I'm doing here is I'm using an angle encoding on the qubit 0 and a phase encoding on the qubit 0, which enables me to encode 2 qubits, two data features on the qubit 0. Similarly, I have encoded 2 data features on qubit 1 as well. So now I have 4 data features already encoded. After the barrier here, I'm entangling the 2 qubits using a CNOT gate. And after the second barrier, I'm again applying 4 other features on the same set of qubits. Now, this enables me to now use 2 qubits for encoding 8 features. And this is still not too deep and can be run on the near-term quantum computers. So it is efficiently encoding my data feature onto the onto the qubits that are available with me. Similarly, taking this approach to the next level, where I want to encode 12 features on the 3 qubits, it's very easy to see that we can really scale this up and have more features encoded into the fewer qubits. But we do need to keep in mind that as we scale up, there is always the limitation of how deep we can go with the near-term noisy quantum computers that we have today. And so we would need to make sure that we are creating a good balance between the number of features we are encoding using this linear operation and the number of qubits we are using to encode our features. As you can see, the advantage here clearly is that we have more dense encoding implemented. We can clearly repeat the same entangling and rotate the layers to have more data features encoded into that. The only challenge is that with every entanglement and feature encoding, we are increasing the depth of the circuit, and at some point it becomes too much of a noise for the quantum device to really retain the value of the data features. There's another encoding technique that can be I would like to talk about today, and that is the higher order encoding. Now, if we think about X as a data set, which comprises of two different features, X1 and X2. Now, if I want to perform a computation on this, I would like to encode this data into a qubit. So let me take two different qubits, prepare them in the 0 state, apply the Hadamard, and then the phase encoding by performing the RZ operation on that. And that way, my X1 and X2 features are now implemented. But that said, if I want to take it to the higher order, as we discussed in our previous problem where the data set was not really easily discernible into two different classes, by taking that to the higher order, I was then able to identify a boundary classification, a linear plane, which would then categorize the two data sets into different categories. So I can clearly perform that using higher order encoding by doing a C0 operation between qubit 0 and qubit 1, and then applying a Z rotation for X1, X2, which will enable me to take this data set into a higher order and then perform the computation. Now, I can continue to repeat these blocks of entanglement and operations for achieving even higher dimensions as required. But we have to keep in mind that with each of these operations, we are increasing the circuit depth, and again have a limitation with the amount of circuit depth we can achieve with the near-term quantum devices. What I showed you here is available as a ZZ feature map in Qiskit today. And if you would like to explore more on that, you can look at the ZZ feature map there. And I would also recommend you to look at the supervised learning with quantum enhanced feature spaces paper to learn more about how we can efficiently encode in higher order. Here is a summary of the different encoding techniques that we discussed today. But again, I would like to highlight that this is just to give you an intuition, a feel of how data encoding can be implemented. There are many more techniques, quite a few research that others have done. It is important for you to understand what is your problem statement and how you're going to implement that into on your quantum machine, on your quantum device. How are you going to encode the data set that you have and efficiently use it for your particular machine learning algorithm on the quantum device is something that you will have to keep in mind before you define or decide on which encoding technique you would be using. Here, if we look at the comparative analysis, you can see that the efficiency of encoding clearly depends upon the number of qubits that are used for encoding the data, as well as the state prep time complexity involved in preparing these states. In case of amplitude encoding, you can clearly see that it's much easier to use amplitude encoding because it will use the fewer number of qubits, but the time complexity involved in preparing the state is a bit higher. So now let's take a look at some of the quantum machine learning algorithms now that we understand how the encoding is done, and we are past the stage of at least understanding the complexity involved in mapping the classical data to the quantum states. Before we go into the quantum kernels, it is important to understand what is a support vector machine. Now, as we have seen previously, we have a data set, two-dimensional data set, which we want to classify between two different classes. Now, in order to classify it into two different classes, I can easily draw a linear boundary, which will classify it as plus sign and a zero sign, and I have my classification done. But I can also draw another line, which is different from my previous line. And I can have multiple such lines based on which I can classify the data. But what is really a good boundary here that my model should define, and that is what my machine learning or the support vector machine would enable me to do. So here in support vector machine, the idea is that I want to identify one clean boundary between the two different data sets such that I increase or maximize the margin between the two different data sets. So here, while my model will learn to have this central line as the model function, it will be important that I maximize this distance between the two data sets and ensure that there is no other data that comes in this particular margin. And it is a clean margin for me to define that my if I see if an unseen data comes to me, I can classify it very easily between the red and the blue data set here. Now, in order to do that, support vector machine has a primal formulation, as can be seen here. It is f of x, where it is an inner product between the parameter, the model parameter vector, and the data parameter, the data features, along with the bias, which is summed into this particular inner product. If we manipulate this particular function and manipulate it further, we have another mathematical model that comes as a dual formulation. And here, instead of calculating the value of parameter theta, we are calculating the parameter alpha. But the interesting part here is that apart from taking a look at the labeled data here, we are performing an inner product between the data features itself, rather than performing an inner product between the parameter and the data vector. Now, if we come back and look at the previous example where we had a mix of data and it was difficult to differentiate between the two classes, we had two different features here, x1, x2. We took it to a higher dimension where we had x1, x2, and x1 into x2 as the data feature. Now, what we have essentially done here is that instead of using the x as the data set, now I have mapped this into a phi of x as the mapping of this data set, and I have a higher dimensional data now available as part of this feature map, which I'm going to use for my machine learning. So clearly, if I replace this phi of x into the previous formula that I have shown, and the primal formulation, that now becomes a inner product of the parameter vector with the feature map vector, with the addition of the bias. And in the dual formulation, now it is the inner product of the feature map with the feature map itself. Now, this is very interesting. This component here, which is highlighted, is very interesting because this is where we can now define, and there exist certain kernel functions, as we call them, where instead of performing the inner product between these feature maps, I can actually perform the inner product between the features themselves and yet get the same result. So this kernel function can give me the same result as a product of these feature maps. And this is called as the kernel trick in the support vector machine algorithm. Let's take a simple example here. Here I have taken phi of x and phi of z as the feature maps. And in this, my feature map results into a higher dimensional equation where which is 1 plus 2xz plus x squared z squared. Now, this is definitely a little complicated for me to compute because it is taking me my computation to the higher dimension and has higher computation cost as well. But I do have a kernel function, kxz, which is 1 plus xz to the power of the whole square. Now, what I can essentially do is, instead of calculating this complex calculation equation here, I can simply perform 1 plus xz and then square the value. And it's much easier for me to compute this kernel function. And the cost of computation is quite less as compared to the inner product of this feature map that I have here. Now, scale this up to the number of high dimensionality that we have in the various feature maps that we have today. it can scale up to infinite level of dimensions as well. And so you can clearly see that it is very difficult to perform this inner product of infinite components and have a low cost computation as well when we have to perform these computations for the feature maps themselves. But the kernel trick enables us to perform this in the lower dimensionality just by computing the inner product between the features themselves and then yet get the same results. Now take this concept into the quantum kernels. Now this data encoding, when we were performing on the quantum device, we took the classical data set and mapped that onto the qubit. What we essentially did was that the classical data was now mapped to a higher dimension. And on the because of the way quantum qubits entangle and perform computations, we are actually performing the computation in the higher dimension automatically rather than performing the computation in the lower dimension. But if something can really be solved using the classical computers at a low cost in the lower dimension, why would we really go for quantum kernels? And that is where we will again go back to the question that I was asked earlier. When do we use which data encoding technique should be used in which use case? There is no clear definition even for the quantum kernels when it is required to be used. But the rule of thumb is that if you are able to solve a particular kernel problem using classical quantum kernel computation itself, then there is no point in implementing the same thing onto the quantum machine. There are, via various studies, it has been identified there are certain use cases for which we do not know of an efficient classical kernel which will help us to solve the problem. And that is where we will go to the quantum kernels, where we map this classical data onto the quantum qubit states, and then we start applying the quantum machine learning or the quantum kernels such that the manipulation is going to give us a result, which can then be applied to the support vector machine to perform the computation classically. And that is what our quantum support vector machine algorithm would be. So it's a combination of quantum kernel on the quantum device and a classical post-processing. Here are a few papers that would be important to understand this aspect, where quantum kernels have been have proved to show efficient execution as against the classical algorithm. So what is quantum support vector machine really? The first part is preparing our qubits in the zero state and then applying the feature map using the first sample. So here I should highlight that the Xi, Xj are two different samples of the same data set. And what we are going to do is take two samples at a time and apply the kernel such that we are able to then identify or learn the value of alpha parameter, which can then be retained for each such combination, and then define a kernel matrix, which can then be used for our support vector machine algorithm classically. So what we are doing here is preparing our zero state and applying the feature map using one such sample data. And then I'm applying another sample data feature map onto the state, the manipulated state. And then what I'm doing is measuring the probability of or identifying the probability of measuring the state of zero after applying the two data sets. What this quantum kernel estimator is really enabling me to do is identify how similar one particular data set is with the other data set. And that is what my probability would be, and my probability will give me the value of alpha. So here I have taken, for example, two different data samples, I and J. For each of these combinations, I am now preparing the preparing the states of phi of xj transpose to phi of xi on a initial state vector 0. And with this, I'm measuring the probability of measuring the state of 0 after performing this computation. With this, the value of alpha that I get will be plugged into the kernel matrix as an element for the combination of those two data sets. And this kernel matrix, which I identify, will then be used classically to perform the support vector machine algorithm and to determine or predict the value of the label. So with that, we come to the variational quantum circuits, which is the next set of algorithms that we would want to focus on. Earlier, we have taken a look at the general supervised learning model, where we have the training data set, which is fed into the model f of x and theta. And this model is then trained well to learn the parameter values such that it is generalized well to unseen data as well. And we can then use it on unseen data to predict the outcomes or the labels of the unseen data. Now, translating that into the quantum machine learning algorithm called as the variational circuit as a classifier, we prepare this data into a state of psi by using one of the data encoding techniques, which is more suitable for of course, my problem area and my data set. So I prepare the state of psi, which is the data encoded into the quantum state, qubits. And then I perform unitary operations. These are parameterized unitary operations that are performed on the qubits. These parameterized unitary operations result into an outcome, which is then fed into the cost optimizers to identify what corrections or gradients need to be applied to these parameter values such that the model will learn the better values of theta and give me better outcomes, which has minimal cost function. These unitary operations that you see are called as variational circuit or parameterized quantum circuits, or also ansatz. So you will see these terms used interchangeably in various literature, but it essentially means that it's a parameterized unitary operations that are performed on the quantum states to manipulate and learn the model such that we can then start predicting the outcomes of the SIM. So this M is nothing but the measurement. So once we perform the operations using these unitary circuits, we will measure the values of the qubits. These measurements are going to enable us to determine the probability distribution of over the possible outcomes, or we can identify the expectation value of the observables, which can then be used classically for post-processing and for model predictions. Now, what we are doing in variational circuit as a classifier, we are really performing a supervised learning to classify the data set into binary class, say here 1 or -1. The first step is to encode the classical data into the quantum state, for which we have looked at various encoding techniques. Then we apply a parameterized model, which is the unitary operations that we perform. The third step is to measure the circuit labels or extract the values from these qubits. And then the fourth is where we are performing the optimization techniques to learn the better parameter values that should be applied to the model. So here in the variational model, we have the first step of data encoding, which we have already seen. And then we have the ansatz, which is really a unitary parameterized unitary circuit, which is our model. It should be noted that designing this ansatz is not a straightforward technique or a step, because it requires us to ensure that the circuit that has been designed is expressive enough to understand the underlying data model or the data patterns and the structures within the data, as well as ensure that this is not too deep, considering the constraints of today's or the near-term quantum devices that we have. In today's quantum devices, I'm not sure if everyone understands that, so I'll try to explain that a bit more in detail. In today's quantum devices, since we have noise, there's a limit to which the circuit depth can be implemented without losing the information on these qubits. Now, we also have the challenge of not all qubits being connected with each other. So when we design ansatz or the variational circuits, it is important that we reduce the requirement of swapping the qubits in order to connect two different qubits which are far away. So that is where in designing the ansatz, it is important that we have enough degrees of freedom implemented so that the model can learn the underlying data parameters, and it is expressive enough where it learns the parameters and performs well on unseen data. At the same time, it is hardware efficient, and based on the hardware topology that we have, it implements the entire circuit with minimal depth that can be implemented. So for example, in the circuit that I have shown here, I have 4 qubits in which we are performing a single qubit unitary operations on the qubits that makes sure that we have lower depth when these operations are performed. And then you can see that we are performing the entanglement, linear entanglement across these qubits with the nearest neighbor, which reduces the need of swapping the qubits. So that way, my ansatz is quite efficient. There is a paper that you can also look at for understanding the usefulness of these ansatz and how it can be designed well for hardware efficient to solve to efficiently solve the problem on today's hardware. Now, once we are done with defining a good ansatz, which will help us to predict the values, well, we will have to now measure the qubits. And this measurement is essentially a non-linear operation that is performed on these qubits. Once these measurements are taken, we take these outcomes as labels and feed that into the cost function. Now, the idea here is, of course, to minimize the cost function. So we feed the cost function into the classical optimizer, where classically it is determined in which direction the parameter updates need to be performed in order to make the model perform better. These updated values are then fed back into the ansatz to use the updated values of the parameters, and the iteration continues till the time the cost function is minimal and our model is generalized well. Now we have 2 functions in Qiskit, the sampler and the estimator. Now, classically, we can now use the sampler function to do a parity post-processing, where the values of these 2 qubits are assessed to determine the binary classification. So if the parity is 0, 0, or 1, 1, we classify the data as 1. And if the parity is 0, 1, and 1, 0, then the input data is classified as -1. Instead of that, we can also use the estimator function on the Qiskit, where instead of using both the qubits, the values of both the qubits, we can ignore one measurement and look at only one qubit, in which we will define that for the poly Z measurement that has been performed on this particular qubit, if the value is greater than 0 or greater than or equal to 0, we will classify it as a class 1. Otherwise, it will be a class 0. Now, since the value of this qubit will be between -1 and 1, it is easy for us to compute this binary classification using the estimator here. Now, once we have the cost function determined, now we can choose that we want a gradient-based optimization done or a gradient-free optimization done. In the previous examples, we have seen the mean squared error metric being used, and we have performed the gradient descent. So we can use the optimization function that is best suited to the class of problem that we are trying to solve. In this case, we are using a parameter shift rule for the gradient estimator, in which we are performing the same circuit twice, once with a phase of pi/2 and second time with a shift of phase, where we are using now -pi/2 instead of pi/2. And based on this parameter shift rule, we are determining what the gradient value would be, and we are using it for the future computations. But one thing here to note is that there are other optimizer functions as well. In this case, I want to call out your attention to the SPSA optimizer function, which is both an estimator as well as an optimizer. And this has been favored quite a bit to run on today's noisy quantum devices because it has shown better performance and less cost of computation as compared to the other optimizers. So if you would like to explore which optimization techniques you should be using, I definitely recommend you to take a look at SPSA. There's also this paper which you can look at into more details for the same. Now let's take a look at the quantum neural networks themselves. Before we start going into the quantum neural networks, let's briefly touch upon the classical feed-forward neural network. Here is a diagram of the traditional or the classical neural network, which is comprised of multiple layers. The first layer is the input layer, as you can see here. This is where my data features are fed in. Now, these data features are then linearly fed into the next level, next layer in the neural network, which is a hidden layer. All these data features are linearly computed into these next layer, and then a nonlinear function is performed before it is passed on to the next level of hidden layer as well. Now, the neural network can have one hidden layer or more than one hidden layer, depending upon the problem you're trying to solve and how your model performs well to the data set you have. Each of these have different parameter values as well, which need to be learned by the neural network over multiple iterations till such a time that your model has again generalized well and will be able to perform well against the unseen data as well. And then we have the output layer, which is giving us predictions of the probability distribution of the predictions of the potential solutions and classes, and that can be fed into our cost function to determine the right direction in which the gradient descent should be the gradients should be moving for feature updates. What we see here is the fundamental unit of a neural network, which is called the perceptron. And as you can see, each perceptron is fed with multiple data features having different weights. This perceptron has two different functions which it incorporates. The first function is a linear function where each of these data features are multiplied with their weights, and all of this is summed to and summed along with the bias to perform the linear function. And then there is a nonlinear component to this particular perceptron, where nonlinear activation function is performed on the linear computation that has been performed in order to determine the more complexities or the higher dimensional complexities which help the model to understand or learn the data patterns better. This is how neural networks really essentially bring out the insights which are difficult to otherwise compute using linear computations. So I do want to highlight that nonlinear activation function is one of the key components of neural networks. Now let's try to correlate the same to the quantum neural network. Now, if we think about a quantum circuit, every unitary operations that we perform is nothing but a linear function. All we are doing is a linear function. So then we need to identify what is this nonlinear activation function component in the quantum circuits, and how are we going to define that? And that is where the measurement comes into play. Now, when we measure a qubit, this is nothing but a nonlinear function that we're performing, and that helps us introduce the nonlinear activation component on the quantum circuits. So either we could have the complete linear function completed and then a measurement done, which brings the nonlinear component to it, or we could have mid-circuit measurements, mid-circuit measurements implemented so that we have the nonlinear component introduced in between the circuits at various points, the way we generally do in the classical quantum machine learning, quantum neural network as well. The other aspect, the other technique that we could employ is using the quantum Fourier transform technique, via which we can have the nonlinearity involved. There are certain papers, research papers listed here, which will be good to look at to understand these techniques better. So now we have the classical neural network and the quantum neural network given here side by side to give you a comparative analysis. Now, in the classical network, neural network, you will see that we have one input layer, and all the input, all these data features are serially fed through different hidden layers, assigning different weights and biases as parameters. and the output of one particular layer is fed as signal to the next layer, not really ingesting the original input data into those subsequent layers. So this is how the classical neural network works. But in case of the quantum neural network, over a number of studies that have been performed, it has been seen that it is efficient to implement a quantum neural network where we have S of X as the data uploading component, where the data has been encoded onto the quantum states. And the U of X is the unitary operation, the parameterized unitary operation, or the ansatz that we are implementing on the encoded data. Now, instead of having the next layer as well as another unitary operation, there is a concept of data re-uploading, which we apply subsequently to each of the unitary operations. So we have the data encoding, then we have the unitary operation, then we have the data re-uploading, and then we have the next set of unitary operations. And that is how our neural networks, quantum neural networks, are designed, and have been, it has been seen that by applying this technique of data re-uploading, we are able to design better universal function approximators using these quantum neural networks. And of course, there is the measurement that is done at the end, via which the probability distribution is computed, and it is then assessed via the cost functions, and the gradient descent is performed to minimize these cost functions and update the parameter values such that our model learns minimizes the generalization error. The next we would like to look at is the quantum convolutional neural network. But before I go to the quantum convolutional neural network, it is important that we understand what is a convolutional neural network itself, which is the classical algorithm. Now, CNNs are really designed well, or these are architectures really work well when we have to work with images and we have to classify or capture certain components of the images to classify it well. So in this particular diagram, in this particular image, you can see that in the entire image, there is a small Qiskit logo that I would like to extract and then classify whether that is a Qiskit logo or not. In order to do that, I will have multiple layers of convolutional layer and pooling layer. In the convolutional layer, what I'm essentially doing is I'm taking the pixelated value of my data set, that becomes my data features, and I'm applying a specific filter. Now, there are various filters that are available. Depending upon the problem that I'm trying to solve, I may have a specific filter that I would like to apply to extract that particular feature. So I apply this particular feature as a, what you can see here is that in a 5x5 pixelated image, I have a 3x3 filter that I'm applying on this data set. I'm superimposing to identify the next value for my next layer. And I slide this 3x3 filter throughout my matrix to get another set of values for my pixelated image. And here you can see that my 5x5 matrix is now reduced to a 4x4 matrix. My next operation is the pooling, where the nonlinear activation is really performed. Now it is the pooling function where I'm additionally going to implement certain functions to further minimize and extract the data features from my from the resulting data set. So what I'm doing here is, instead of applying a filter, now I'm applying a function. It could be a maximum function, or an average function, or a summation function. But by applying this particular function, I'm now extracting the feature out of this 4x4 matrix into a 2x2 matrix. So I take these 4 cell values, and the maximum, in this example, I have applied the maximum. So I take the maximum of the 4 values and extract my feature as 3 here. Similarly, for the remaining data sets, I'm able to extract the maximum of the values to now reduce my data features as a 2x2 matrix, and determine that now with the small relevant feature data sets, the relevant features that I've extracted out of this image, I can now classify easily whether this particular image set classifies as a Qiskit logo or not. It should be noted that these convolutional and the pooling layers can be applied multiple times for me to really extract my data features well. And at the end of these layers, convolutional layers and pooling layers, I have a fully connected neural network layer, which where all the input data features or output of the pooling layer is actually fed into all of the new perceptrons in the layer. And then I get a probability distribution, which helps me to classify the data set. Now, the similar thing cannot be implemented as is in the quantum neural network, but taking that concept to the quantum convolutional neural network, what we are essentially doing is that instead of applying that filter and sliding it through the data set, I'm now applying a unitary operation to a local set of qubits. And you can see that I'm feeding either 1 or 2 qubits to each of these unitary operations. And in the next layer, I'm sliding the unitary operations to the next 2 set of qubits. That helps me to induce the sliding filter capability that we had seen in the convolutional neural network previously. Once I have the convolutional layer implemented, then comes my pooling layer. And in the pooling layer, I bring in my nonlinear activation component by measuring one of the qubits. And based on the measurement of this qubit, I apply another unitary operator on the second qubit that introduces the entire nonlinearity in the pooling layer. And I get a fewer set of qubits then which help me extract the more relevant features out of the initial data set that I had entered. Now, I can have multiple such layers of convolutional and pooling data layers, as you can see here. And at the final outcome, I can have my my fully connected layer, which is nothing but a unitary operation that is performed on these qubits. Now, either I can measure all the qubits that are coming out of this fully connected layer, or I can ignore some of these qubits and perform measurement only on certain qubits that will introduce more non-linearity. And the measurement then helps me to get a good probability distribution and then help me to classify whether the particular input image is that of a cat or a dog. Now, what I would definitely like to highlight is that in QCNNs, QCNNs can be implemented on near-term hardware because it has lesser number of layers that are required to be implemented for the number of parameters that we have. But they also don't suffer from the problem of barren plateaus. When I say barren plateaus, it is similar to what we see in the classical neural networks, where there's a problem of diminishing gradients, where but it is not, the root cause is very different in the quantum world. So what we are essentially doing here is that we are performing computations on the local qubits and not on the complete global set of qubits. And that is why there is the challenge of diminishing or gradients or the barren plateaus is reduced or avoided completely. And we can, because of the non-linearity that we are introducing in the pooling layer as well, we can perform the measurements and ensure that we are not really reaching a state where the barren plateaus are resulted. Below is one paper that you can definitely look at to understand more on the quantum convolutional neural networks. And with that, I come to the end of today's presentation. These are some of the references that I would recommend all of you to take a look at. There's a complete Qiskit Global Summer School that was conducted in the past, which was focused on quantum machine learning. So that will be a good source of getting to the fundamentals of quantum machine learning. But there are other sources as well, which you can take a look at to learn more on this. With that, I can now start taking any questions that you may have.
Thank you very much, Mrs. Guncha Malik. That's a very useful session. We'll just take a few minutes for the audience to have any questions.
Sure.
Excuse me, ma'am.
Yes.
Actually, I don't know whether this question is valid or not, but still, the question is, you shown one diagram where we were having 8 features that are encoded using 2-qubit system,
Mhm,
and there are 12 features which are encoded using 3-qubit system.
mhm.
So, how to identify the number of optimum qubits?
Again, so it's not a simple formula that I can give you, Harsha. I would recommend that you play around with the circuits and understand for a particular quantum device based on the specific qubits that you're using on that device. What is the depth of the circuit you can really have, and then define whether for the problem that for the algorithm that you're going to solve, can you uh, encode the data into the states such that it can be easily read and manipulated by the algorithm itself. Um, in case it is not clear, the hardware devices have qubits which have different performances as well. So when you are really building a quantum circuit, there's a transpilation that happens, which looks at what are the different qubits available, how close they are, what is the proximity of those qubits, what is the performance of those qubits, and that transpilation process actually then remaps your entire circuit to a lower level circuit, which defines which specific qubits are going to be used for your computation. So when you're designing your encoding mechanism, it is important for you to understand whether the encoding that you implement is going to be efficiently implemented on the hardware device that you're using or not. Although you don't have to do that lower level mapping, Harsha, there is, if you take, for example, Qiskit as the SDK, it performs that automatically if you call the function, but you still need to understand and play around to assess whether the encoding that you've done is going to be efficient or not.
Okay, ma'am. Thank you so much. Ma'am, may I have your mail ID, please?
Let me type it on the chat. Maybe that will be easier. It's gunchamalik@gmail.com.
Okay, thank you so much.
Any other questions from the audience, please? Okay, ma'am. Thank you very much for your valuable session.
All right. Thank you, everyone.
Move on to the next session with the.
Have a good evening. Bye.
Thank you. I'm honored to introduce Dr. V.P. Ramesh, a professor in the School of Mathematics and Computer Science at the Central University of Tamil Nadu, Tiruvarur, India. Dr. Ramesh has long teaching experience and his expertise spans algorithms, quantum computing, and mathematical foundations of computer science. He has guided many postgraduate students and has contributed research in the area of computational sciences, focusing on the design and analysis of efficient algorithms. Today, he will deliver his lecture on algorithms for quantum computing. His deep academic insight into the mathematical underpinnings of computation will help us gain clarity on this crucial area of study. Thank you.
Hello, sir. Can you hear me?
Yes, yes, Miss. Yes, doctor. We can hear you.
Yeah. Just give me a second. I am connecting now.
Okay, sure.
I'll connect my video also in a couple of minutes.
Yeah. Dear audience, thanks for your patience. Just hold on the line. He's on the process of joining. We still have a few minutes for the actual schedule. Thank you. Sir, we are able to see your screen.
Yes, sir, it's visible.
Okay. Thank you. You're able to see the screen?
Yes,
Yes,
sir,
sir.
yes, sir.
Yes, sir. We are able to see your screen and
Yes.
your audible also.
Yeah. So I'm sorry, there is a small issue that I have a problem in streaming the audio. So I'm connecting two devices for sharing one, and for speaking I'm using another device. So you will see multiple screen because of
problem,
yeah.
No problem. No problem.
Okay. So we can start now. Okay, let me switch on my video.
Yes, sir. We can.
Okay, so yeah. So good evening to all. Thank you for this opportunity to Professor Palnivel and the other colleagues for the opportunity to talk in this FDP program. So yeah, so I just want to know that you are all faculty members. So I just wanted to understand the background. Okay. So the title of the talk is Algorithm for Quantum Computing. So in other words, algorithm for scalable computing. So I have some theoretical. I have the content of the talk is divided into two parts. One, I have a theoretical background on how one design an algorithm for scalable computing or quantum computing. In other words, when computing becomes more intensive for a large number, for like big data and all that, how do we algorithmically play a role on deciding an algorithm? That's a theoretical questions. And then I also wanted to show one of the examples of image classification problems where one can apply algorithmic technique to perform better. Okay. So how many of you know Python, right? Am I right?
Yes, sir.
Yeah. So we all know, is there any limitation of Python? Meaning Is there a problem in which you are unable to solve it in a Python, something like that, or you have a code but it is not giving an output in Python, irrespective of what machine you are using, maybe parallel machine or whatever? Have anyone encountered such issue? What I'm asking is, you have a computing task, you have written a nice code, okay, and you have a nice computer, but you are used in Python. I will use Python as a software to write the code, but due to some reasons, maybe you may not know what is the reason, but your code is not giving an output for you, or in a desired time the code is not giving an output for you. Have you faced such issues? Let this talk be interactive talk, okay? Otherwise, I'll keep talking at the laptop and you hear and nothing will happen, okay? So please interact. Any idea? No. I think people are online, right? Hello?
So far, I have not encountered such case, sir.
Okay. Okay. So imagine that, they say let's say there is a computing and it's giving a small error at every iteration. Let's take a very basic thing, okay? Very basic thing. Suppose if you want to estimate log x in a computer, okay? Take Python, find, what is the Python function to write log x, and keep finding x for larger number. Okay, log to the base, some base, you can fix any base. Let's say 10 is a base. So when you keep computing, you'll always see that at some point of time, the machine says NAN, or the machine says runtime error, or the machine doesn't give any output at all. This is, I think everyone might have seen that, okay? In a very common issue, okay? Even though if you are running in a very good computer, okay? So the hardware is good, algorithm is okay, and then algorithm stand algorithm, because log x is already defined in Python. So you cannot do anything with that. But the machine is not giving an output for you. So the reason is that the algorithm is not efficient for a large number. So that's why you're coming into quantum computing now. So the amount of computing that you are doing is quite a bit. In that case, what is the algorithm role for doing the computing? Okay. So good that I guessed it. So I prepared a slide which is elementary in the beginning. Okay. And then I want to know how many of you are mathematics background. Is there anyone who is from mathematics background? Or everyone is
Yes,
engineering
Yes, sir.
background?
Yes, sir. Yes, sir. Some people is from mathematics background.
And others are?
Others are from engineering background.
Okay, so can we say majority are engineering background?
Yes, sir. Yes.
Okay, good. Okay, so yeah, then my slide will be of that kind. So I'll give a very simple example that is appearing nowadays in most of the exams. Okay, that is called Tower of Hanai problem. That will tell you what is the complexity of a problem. Okay, and then the overview of talk is something like this. Maybe manipulation sum and application of Gauss trick I'll skip because it is mostly mathematical. So I'll skip that. I'll not bring into this in this lecture. But I will talk about the complexity of Tower of Hanai problem. And then I'll introduce the complexity theory. I'll introduce what is P versus NP problem and the history of NP problem. And then we get into why such errors are happening in the machine, which is the background of quantum computing. I'll show you some of the examples where the code fails, irrespective of good hardware and good resources good space, because hardware is not really enough. You also need a space to do the computing. So good space, good hardware, but because of algorithms, certain machines are not performing well. So that is the motivation for quantum computing. And then I'll show you some examples. Okay. So this is the Tower of Hanai problem. So this is a mathematics problem. Okay, so the problem is something like this. You have 3 towers and there are disks. Okay, the disk will be, if you see the disk size, it is lowering. So that is the largest disk is at the bottom, second largest is at the top, and then it keeps going. Okay. This was designed by a king in France. Okay, because he thought that some of his ministers are not thinking much. So the king designed this problem in the way back, and then it becomes a problem of Luca. Okay, and Luca is the one who proposed the solution for this. Okay, But this problem was defined by a king without a solution. The king asked his ministers to go and find the answer for this. Okay? So here is the example. The king's problem is following. Okay, there are 3 towers. Imagine that there are n number of discs on one of the towers. N discs are there, not 4. It is n. Okay, let us make it n. Some number of n. 1 or 2. N can be any natural number. The problem is you have to shift these discs to one of the other discs, either the two empty discs. Rules are the following: 1, you cannot lift more than 1 disc at a time. 2, you cannot put a bigger disc on a smaller disc. In other words, a smaller disc can go on a bigger disc, but bigger disc should not go on a smaller disc. So you can see this. Okay, the order of the disc should be in decreasing order. Okay, so that the king asked how many number of moves you have to do to shift n number of discs from one tower to another tower. And the king goes on to ask, suppose if I have 32 discs on one of the towers, what is the estimated time for someone to perform this task? Okay, so the king had a hint of the answer. Okay, that it is like a large number, and the king thought that it cannot be done by one's life. I mean, 2-3 generations has to work together to finish this task because of complexity in the process. Okay, so it is as follows. Okay, that is the question. So questions will depend. You have a tower with a lot of discs. You have to shift all these discs to one of the other discs. Rule number 1: you can lift only 1 disc at a time. That means you can take 1 disc and put it in the other disc, other rod, and then lift the other disc. You cannot lift 2 discs or more than 1 disc at a time. Rule number 2: you cannot put a bigger disc on a smaller disc. Okay, so that is the problem. So it goes on like this. Okay, so the logic is very simple. Suppose n is an n number of discs. Okay, the logic is very simple. Suppose if you have 1 disc, then I can move it in 1 move. So I lift the disc and put in other tower. Okay. Now suppose there are 2 discs in the tower. First tower, rather than 4, if you have 2 discs, what you do is you lift the smallest one, put it in another tower, put in one of the towers, empty towers, and then lift the largest one and put in the other empty tower. Therefore, one move for the smallest one to go here, and then the second move for the largest one to go to the third tower, and then again the smallest tower has to go to the largest tower. So if you have two discs, it takes 3 moves to complete the movement. Is it clear?
Yes, sir.
Yeah. Suppose if you have 3 discs, how many moves you need?
7 moves, sir.
4?
15 moves?
How do you say that?
Because 2 power 4 minus 1 moves.
Okay, suppose we n disc then.
2 power n minus 1 moves.
2 power n minus 1.
So how do you know that? It's a guess, right? So how to
No,
prove
sir.
this?
The minimum number of moves recorded is 2 power n minus 1. If you have n moves, the minimum number of moves recorded is 2 power n minus 1 moves.
Correct. Yeah. So if you look at it very clearly, suppose if you are going to shift 4 discs, what you have to do is first you have to shift all first 3 discs to one of the towers, right? Then only the largest disc
Yes.
can go to the next tower, right? Therefore, what does it mean? That means you have to shift 3 discs to one of the towers and shift the 4th one to the empty tower, and then again shift the the 3 discs to the largest disc, right? So theoretically, if you look at it, Hn is Hn minus 1 plus Hn minus 1. Can you say that? Where Hn is the minimum number of moves to move n minus 1 disc. Okay. Is it clear? Can we say this? Hn is equal to 2Hn plus 1. That means what? Suppose we have n disc. Hn is the minimum number of moves for moving n disc. Now to move n disc, first we have to move n minus 1 disc to the tower. One of the towers, right? Only then the nth disc can go to the empty tower, right? Yes or no?
Yes, sir. Yes.
Yes, sir.
Hn minus 1 first, and then 1 plus 1 is because the largest disc will go to the next one. So that is it. As one of you guessed, it is like, I'll skip this. Yeah. As one of you guessed, it is 2 power n. Okay. Now, what do you know as an engineer? What do you know about 2 power n? What is 2 power n a good number to estimate in a machine? So in school days, you have studied, exponential functions are going very faster, right? So engineers always want the logarithmic function to do this because logarithmic functions are very slow. They also go to infinity, but they slowly go to infinity, whereas the exponential functions goes to infinity very fast. And you also studied in your calculus, you teach in calculus that exponential function is the inverse of log function, right? So when you have 2 power n, the inverse of 2 power n is log to the base 2. Therefore, if log goes very slowly, the inverse of that is very fast. Therefore, 2 power n goes to infinity very fast. So they call 2 power n as a exponential function. Engineers call it as a non-polynomial function. Am I right? Engineers call that as a exponential function as a function which is not a polynomial function. Because as per the engineering terms, if you do anything, you want the output in a polynomial time. If you have anything in a non-polynomial time, it is of no practical use because it cannot be implemented in a product. So you always want, for any product, any software, whatever, everything has to work in a polynomial time. Therefore, what does it mean? This question tells you that the king has given a non-polynomial time question, which is very hard to solve by a machine. Because even if you have a software to run this, when n becomes larger and larger, even if machine is shifting it, it takes a lot of time. Okay. Suppose n is 32. What is 2 power 32? One can imagine. What is 2 power 32 is a big number, right? So 2 power 4 is what? 4, 8. So you have 16, and then that means what? 16 to the power 8. So you can just see that even if you take 1 minute, 1 second to shift a disk, if n is 32, it will take one's lifetime to move the 32 disk to the other door. So practically, this kind of problems cannot be solved in a machine as of now, whatever the machine that you have. So we'll come to ChatGPT a little later. Even ChatGPT cannot solve all the problems as of now. It can solve some trivial problems, but if you give a tricky problem like this, ChatGPT will get confused. In other words, we can also generalize this idea. Not only this problem, if you have any problem which takes exponential time to solve, that means 2 power n or 3 power n or whatever, those problems are not going to be solved by ChatGPT. That is for clear. Okay, so we call that as a hard problems in computer science, or other words, we call in computer science they call it as NP problem. That is called non-polynomial time. We'll come to that. Okay, I'll skip this proof of this. Okay, so what is it all about? That is a question here. So Thiruvalluvar says, the feather Pilive Sagadu Machirum Apandam Salam. That means the feather of a peacock is light, very light, but if you put too much on that, the vehicle chase will break. Okay, so something like that. If the error may be very small, but if you do n number of iterations, what will happen? It will dominate the product. So small things can lead to a big disaster. That's what theoretically we call it as in machine learning, in computing. When you have a quantum computing, even small errors has to be tolerated because you are doing a huge quantum of computing. Therefore, when large numbers, if you large error, the small error will lead to a big error. That's what it means. So feather of a peacock is light, but if you put huge number of peacock feathers, the vehicle will break. That's what theoretically Thiruvalluvar says. That is what the philosophy of this P versus NP problem. Okay, so this has a huge application not only in engineering but also in mathematics. Many of the mathematics people also work on this, especially number theory guys, because when they want to compute something for large primes, they need algorithm for efficiently to calculate that. Similarly, statistics and probability theory people use for machine learning and all that. Numerical analysis is another one. So apart from computer science, this has a huge application in maths. This concept of quantum computing has a huge application in mathematics as well. If you go and see some of the greatest mathematicians so far, Ramanujan, Chawla, Harishchandra, S.S. Pillai and all that, all of them have worked on something related to this. And if you see this, if you see none of them is an exponential function here. If you look at it carefully, none of them is an exponential function. All of them are polynomial functions or logarithmic functions. If you see this here, except the left-hand side. Right-hand side will be, for example, if you see the Ramanujan's theorem, figure the third part, you see log of P of S to the P of Sn of n. That means it's an exponential function. Now, logarithm of an exponential function, what Ramanujan gives is, Ramanujan gives an estimation in terms of a polynomial. So in terms of polynomial, he is giving an estimation for an exponential function. So this is one of the historical problem in mathematics, especially number theory, that people wanted to tackle exponential functions through polynomials. Okay, and all this because of computer science guys, because they want to solve. I mean, they want to have quantum computing involved in, involved in many applications. Okay, so I'll just define what is this. So this is the problem defined in Clay Mathematical Institute. Okay, in this one. So the field medalist Steve says that P versus NP problem is a gift to mathematics from computer science. So what is P versus NP is, P and NP are sets. Okay, imagine that P is a set of problems in the world. NP is another set of problems in the world. Okay, it could be any problem. Don't worry about only computer science problem or anything. It could be any problem. Now we say a problem belongs to P, a problem belongs to NP based on the character of the problem. For example, I have a problem. Let us say, given a natural number, I want to find out whether the natural number is prime or not. Suppose, or in a computer science background, this is a mathematical background. In computer science background, you have an X-ray. Yeah, is there any question? Anyone has a question or what? Hello? Okay. So yeah, let me start again. So P versus NP. So P is set of all problems of some character. NP is set of all problems of some character. Okay. So character is the following. Let's say for mathematical example is, someone give you a natural number. You want an algorithm to see whether the natural number is a prime or not. Okay. In computer science background, someone give you an image. Let's say an X-ray image. You have a huge number of X-ray images in your database. Now you want to have an algorithm to compare the image with the database and say that whether the X-ray image, can you conclude anything on the X-ray images? That means, can you conclude that the patient has COVID or not, or pneumonia or not, whatever, something, okay, based on your database. So you have, let us say you have 10,000 images in your database. Someone comes with an X-ray image. Can you compare your database and see what is the probability that the patient has COVID or not? Okay. If you see both of them, you have a huge computing involved in both. Okay. And huge computing involved, but one problem is less complex than the other problem. For example, comparing the image with the 10,000 X-ray images and giving an output is an easy problem. It belongs to P, because in other words, there is an algorithm called CNN, convolutional neural network, or many algorithms are there. There are algorithms which are polynomial time. In other words, there are algorithms which can give output in a polynomial time. Okay. Whereas if you take given a natural number to see whether natural number is prime or not, as of now, we have n number of algorithms now. Then even if you go to this Python, it has an algorithm. But all these algorithms are not polynomial time. They are non-polynomial time. In other words, they are harder problems. Their time is exponential time. Something like 2 power n you saw na, sometime like tower of n problem. They are mostly having exponential function as the time function. So in other words, primes, determine a natural number is a prime belongs to NP because it is non-polynomial. Given an X-ray image, the task is to design an algorithm to find whether the X-ray image, the patient has COVID or not from your database of 10,000 images is a polynomial time algorithm. Okay. So the complexity of problems are divided based on the complexity of its nature. What is the complexity? Time taken by the machine or a human to solve the problem. Okay. So P is set of all problems which has a polynomial time algorithm. NP is set of all problems which has non-polynomial time algorithm. It is a theory from computer science. So we know that P is subset of NP. Therefore, what does it mean? If I have a problem which can be solved in polynomial time, then I can also solve in non-polynomial time. That is very easy. Santanam strategy will work. He says, keep that model in one place and then move it. Unnecessarily, he moves around and then say, why you are moving the bag? Na? There's a joke, right? Like that, you can do a computing with unnecessary movement. Then the polynomial time algorithm will become an exponential time algorithm. So all the problems can be solved by polynomial time can be solved by non-polynomial time. But the converse is not true. One example is primality is an example, or tower of Hanai is an example. Therefore, the conjecture is P is equal to NP. Okay. If someone proves P is equal to NP, so P is equal to NP, then then machine should be able to do everything. So therefore, as of now, P is not proved to be equal to NP, and therefore, ChatGPT is not the right one. ChatGPT is an intermediate product. It cannot solve it. It cannot do everything. Okay, ChatGPT has limitations. It can solve only few problems. So in other words, simple tasks like creating a website, creating a database, ChatGPT can do. Okay, but given a natural number, whether natural number is prime or not, ChatGPT cannot do. Or given 10,000 images of X-ray images and giving a X-ray image which is nowhere related to this 10,000 images, something like maybe let us say an X-ray image of a monkey, let us say, nowhere related to human X-ray images, can ChatGPT give a recommendation for the monkey, whether the monkey has COVID or not? Whereas a doctor can do that if he is intelligent, but machine cannot do that. So ChatGPT is still a much lower version of the expected this. So Clay Institute has given $1 million to solve this problem. If you prove P is equal to NP, then so Tower of Hanai problem is only a trivial problem. In computer science, they have travel salesman problem. Sudoku, for example. Sudoku is also an NP problem. That means not all Sudoku can be solved in polynomial time. Okay? What you see in the papers, newspaper and all that, they are all simple Sudokus. There are harder Sudokus which are non-polynomial time algorithms. Okay. Any question here as of now? Any questions? Is it boring or are you following what is happening?
It's going good, sir.
You are able to follow? Okay.
Yes, sir.
Any
Yes,
question?
sir.
Okay.
No, sir, you can proceed.
Okay. So you are clear with the polynomial and non-polynomial time, right? So if some faculty members who are interested in doing research in this area, you can go and see these areas. There's historically people have done from 1936, many engineers have worked on this problem, trying to prove one after the other. The last one is done by IIT Kanpur fellows, Agarwal, Khayal and Saxena, who proved that primes is in P. So they have theoretically designed a method to decide whether a given natural number is prime or not in polynomial time. But as of now, it is not implemented in any machine. It's only theoretically proved that it is possible to create one. But they are computer science guys, okay? And it is published in Annals of Mathematics, which is a very prestigious mathematics is a very prestigious journal in mathematics. But these guys are coming from computer science department in IIT Kanpur. So they have theoretically proved that one can design algorithm, but it is still not implemented in the machine because there are a lot of theoretical clinches that one can handle this. Okay. So this is historically what people have. I mean, these are some of the milestone inventions in this area. If you're interested, when I share the slide, you can see this. Okay, so I'll just do a little more rigorous, for both, in terms of geometrically, I tell you how one can do this. Suppose tomorrow you are having an algorithm to do a task. How do you do the analysis of the algorithm? Designing of algorithm, all of us do that. The critical part is analysis of algorithm. To say whether my algorithm is in polynomial time or not is a question, right? So even you can take a simple, bubble sorting algorithm. If you are a computer science guys, okay? See whether that bubble sorting algorithm is a polynomial time or not. How do you do that by polynomial time? You have to just look at it, what is the time it is going to take, or how many iterations is going to take, how many steps are going to be involved, like we did in the Tower of Hanai problem. You have to theoretically study that and estimate a function for that. Let's say Hn can happen. Okay. And when your Hn happens to be polynomial, then you can say that your algorithm is polynomial time algorithm. If Hn happens to be a non-polynomial, especially exponential, then you say that it is exponential function. Okay. So there is something called logarithmic function, which is the best one. That is better than polynomial. Okay. So all of us want logarithmic, algorithm which can give output in logarithm, because logarithm is a very interesting function because it goes very slowly. If you take log to the base 10, okay, then what is log to the base 10 of 10 to the power 6? Is 6 1. That means in 6 iteration you can solve 10 to the power 6 numbers of task. So if you have an algorithm which can give an output in logarithmic time, that's a fantastic one. Okay, your publication you can publish in a huge big journal. Okay, in a good journal. Okay, so logarithm is ideal to have, but many problems are not logarithmic in the world. Okay, even machine learning, okay, even human learning is not logarithmic, right? If you look at how you learn the subject, okay, it is not logarithmic. It is kind of, a little more, very different, okay? But it is kind of logarithmic in some sense that learning is always slow. We take time to learn. There is a logic behind giving 5 years for, or 6 years for doing a MTech in engineering or MSc in mathematics or physics or chemistry, and then 5 years for PhD, because there's always time-consuming process. Okay, so we axiomatically think that learning is logarithmic, but if you look at it in real life, but learning is not certainly exponential, except in movies. Okay, so machine learning, we expect that it learns in a very fast time, but still it's polynomial time only. So it's not exponential time. So if someone can decide, I think in that movie they say, one get a robot take a book and then swipe it and then say it has read. Okay, that's not possible at all. Theoretically, it's not possible. Okay, so it's only movie for cinematic things they have used it. Okay, so even now, so what I'm saying is, human learning itself is not logarithmic. Okay, so idealistic is to have a logarithmic algorithm for solving any task. Okay, but ideally it doesn't work. So the next best is polynomial time, and the worst is exponential time. At least if you understand this, then complexity theory will be following for you. Okay. Okay. So what does it mean by this? I just give you, don't worry about the notation, because if you work in complexity theory, these are all notation made by the engineers. Okay. But I'm not going to look at it because if you know complexity theory, then you may follow others. It's okay. Don't worry about that. What this graph shows is, if I take 1 as a function, okay, constant function, then you can see that log dominates at some point of time. Even log n dominates. Even c times of log n dominates that. You can see what do you mean dominate means what? Its values are going beyond the function 1. So this is the function 1. I don't know, I think I cannot show that. Right? You can see a dark line parallel to x-axis sitting. That is the line, that's the function y equal to 1. And you see the other functions are y equal to 0.4 log n, 0.9 log n, so on and so forth. You can see that even 0.4 log n is dominating the line. So let's take a little more complex function. Y is equal to n. Okay, that is y equal to x. You can take polynomial. Y equal to x is a polynomial, straight line passing through the origin and things like that. You can see that log will dominate this also. Log is dominating this. You understand? C types of log n is dominating this. Okay, so what does it mean? If you look at it, theoretically, what we are saying is, even log is a very slowly increasing function. We know that n goes to infinity before n log n. We know that. Okay, before n log n goes to infinity, because log n will slow down that one. But still, at some stage, n log n will dominate. That is what we are trying to show here. So we say that you might have seen as an engineer, you might have seen that n is equal to small o of n log n. Okay, I use a symbol belongs to because there is some reason for that. But most of the engineers use equal to. N is equal to n log n. That means what? N log n can dominate n. That's what we mean by this. Okay? In other words, n over n log n, will go to 0. That's what it means. That means, okay.
Sir.
Yes. Yeah. Yeah. Yeah, tell me, I can hear you.
Sir, we can continue, sir, please.
Okay. Okay, so, and so on and so forth. And then we also show that, okay, there is a symbol missing here. Small o is missing in the top of the graph. So you can see very clearly that the left hand side is the polynomial function, n to the power, some pi. Okay. So if you take, you can take n square, n cube, n power 4 and all that. These are all polynomials. Pi is irrational anyway, but we just take it for because see, if you see most of the algorithms, certain functions are not inevitable. One is log, another one is pi, e, and all will come naturally. Okay, so we try to study certain functions, how they behave. This clearly says that 2 power n will dominate all the polynomial functions. Okay, in other words, polynomial functions are better for algorithms. Okay. So these are some of the examples. Let us not worry about this. And then we go into this, certain transitive properties. I don't know whether this will be useful to you or not. If you are a theoretical computer science guy, this may be useful to you. What it says is, if you have a function, so if you say f belongs to small o of g, means, in other words, what it means is d goes to infinity before f goes to infinity. Okay. In other words, if you take a rational function f by g, then it is going to 0. Okay. Why you want this is because if you have an algorithm, whose function is f, and if you have another algorithm which function is g, okay, then you compare the two algorithms to see who is better. You always do, na? Certain algorithm gives fast output, certain algorithm gives output little slower, right? So this is why we compare the two algorithms. So when you have f and g as the functions coming out of the two algorithms, then how do you compare? How do you analyze the algorithm to say which is better? This is how we do that. If f belongs to small o of g, it means that g is a better algorithm than f. Okay, you understand what I'm saying?
Yes,
Okay.
sir.
Yeah. So that means the algorithm with the g as a function, algorithm with the f as a function. If f is belonging to small o of g, we say that algorithm with the g as a function is better than f, because the very simple reason is what? That g goes to infinity before f goes to infinity. That's the simple reason. Okay. Yeah. So we also have other properties of small o of n. So the properties are, if you compare the slowest function, which is log n of polynomial n power 5, I take an n power 5 for simplicity. Okay, don't worry about n power 5. If you see the function here, logarithmic of n power 5. Okay, what is important is log. We can see that n log n can dominate log n. Okay, so this is like often very not easy to guess, but graphically we are showing this that it is easy to guess. Okay, and then so why I'm showing all these examples is a motivation for doing this. Okay, this is how theoretical computer science guys who work on theory for quantum computing will analyze an algorithm. Okay, and their theorems will be something like this. They use big O notation, small o notation. You see omega notation in somewhere here. Yeah, the first one. Chawla, Harishchandra. Yeah, Harishchandra has omega notation and all that. So these are the notation. Even this guy, I showed this Agarwal and Saxena, right? They also have such notations. Okay, so these notations is a beginning stage for is a what do you call is a starter pack for someone who wanted to work in quantum computing. Okay, so we have done a paper in Ramanujan Journal of Mathematics to say how someone can simply represent all these notations using simple graphs. Okay, if you are interested, you can see the publication. There's a lot of graphs, and we have also shown that what is the bubble. We have taken bubble sorting algorithm and shown that what kind of complexity it has, whether it is polynomial time or non-polynomial time and all that. Okay, so you can see that someone want to work in analysis of algorithm, this is a very good place to start. Okay, yeah. So say and so on and so forth. Okay, so even if you see log, we know that n will dominate log. That's what you are seeing here. Okay, so log is this and n is dominating this at some stage. And similarly, one can also think of, so big O is another very important notation, very important notation. So I forgot to define it. Yeah. So how many of you are comfortable with the big O notation and small O notation? Are you comfortable, or is the first time you are hearing? Mainly mathematics students may not have heard this, right? I mean, mathematics teacher might not have heard this. Is understanding clear? Is understanding fine?
Yes, sir.
So engineers, are you all comfortable? Have you heard? I mean, you guys have heard about big O notations?
They were used for representing time complexities.
Right. Complexity, right? Time complexity, space complexity, whatever, right? So you guys know the difference between small O and big O? Okay. So at least you guys have used for representing time complexity of something, right? So in fact, it is not only for time complexity, it is true for any complexity, time or space or whatever. You have an algorithm, certain algorithm are measured by time, certain methods are measured by space. That we know. Yes or no? We know that. For example, a simple a idli making machine will worry about time because you make idlis in time. Okay. Whereas if you want to manufacture a aeroplane, it is going to take a lot of space because the aeroplane manufacturing will take huge space, right? So generalize it now. There are some problems which are time sensitive. There are some problems which are space sensitive. Quantum computing is mostly to do with both space and time because you have a huge quantum of computing to be done. Therefore, you need a lot of space to store and retrieve and recall and do that. So for generalize it now, all these notations are used for both space and time complexity. Okay. So the difference is very simple. Big O is a very weaker form of small o. Okay. In other words, it is good to have small o, but if you are not, small o is very difficult to find. So people go for big O. Big O is weaker. Okay. Whenever if you write F belongs to small o of G, so what does it mean? What does it mean? Whenever you write F belongs to small o of G, then you can also write that F belongs to big O of G. But the converse is not true. Okay. That means if F belongs to big O of G, then we cannot say that F belongs to small o of G. You understand? Okay.
Yes, sir.
Yeah.
Yes, sir. Yes, sir.
So practically, if you see that, I have not seen any mathematics theorem or any computer theorem with small o because they are very complex to have. Normally, people use big O. If you see this, even Ramanujan, everyone has done with big O. Okay. So now, so we get into this big O notations. So what it means is you can do both actually. If you see here, if you see that n dominates the square root of n. If you see this, n dominates square root of n, and you can also make n to dominate log n. Okay. Similarly, you can so on and so forth. You can do this. Okay. You can take 2n is also a polynomial function. 3n is also a polynomial function, but you can play with things and then give them dominated. Okay. So and so on and so forth. So n square is again polynomial x square. We use n square here because it is easy to understand for engineers. Normally, if you go to the papers, they use x square. Okay. So these are all polynomial functions. You can see that x square plus 10 belongs to big O of x square. Okay. So that's what we say. But that's what I'm writing. But n square plus 10 does not belong to small o of n square. That itself is a counterexample for you. That big O is a weaker form of small o. Okay. So there are other notations like you have seen the Chawla, Harrison has done this. So this is omega and all that. Okay. So the omega notation is that if you look at it, you should be able to. So very simple case. Okay. So suppose there are, it's something like a sandwiching. Okay. Suppose there are 3 vehicles going in an order. Okay. And every time you see, let's say there is 3 vehicles in line, and if one vehicle is going in the middle, so one vehicle has to go in the middle, and 2 other vehicles are going by side. Suppose the speed of both the corner vehicles are, slower than the middle vehicle, okay, or faster than middle vehicle, whatever you can take. Then the speed of the middle vehicle is bounded by these 2 guys, right? That's how we do sandwich theorem. We say that, right? Or you have studied in engineering mathematics that sandwich theorem. A less than B less than C, then B. The bound of B is impacted by A and C, right? That's what is omega notation is. You often have 2 functions to bound it. Okay. So I'll skip this. So this log of log, you can try. Okay. Log of log also you guys can try. This is some of the fundamental questions that you have to ask. How is it, I mean, having a logarithmic function itself is good. Having a logarithmic, having a function, having a task to solve, having an algorithm which takes log of log time to solve a task is much, much better because log of log is a much slowly increasing function. We know that, okay? So, but this says that how do you scale it up? By using log of log, though log of log is below log, but you can always, scale it by linear multiples of that, 4 times of this, 8 times of this, and 6 times of this, and so on. Therefore, given for all log n, you have a C such that C will dominate, C times of log n will dominate the log n. Okay. But if you look at the hierarchy of these two functions, log is faster than log of log. We know that, right? Log of log is much slower than log. But one can create, for every n, one can create the omega here. That's what I'm saying here, right? So other way around is very easy. Log of log n will belong to small o of log n. We know that. There's no doubt about that. Log of log n belong to small o of log n. And log of log n will not belong to big O of log n. So we need other notations to compare it. Okay. So the next weakest one is omega notation, where we can always bound a slowly increasing function, which is log of log n, to dominate the faster function. So it's something like, tortoise dominating the rabbit. Log is like rabbit. Log of log is like tortoise, but tortoise goes slow. But you say that, if you constantly tortoise works, then it can dominate the rabbit, right? That's how the story is, no? So something like that. Okay. So the domination should happen for functions which are faster by a smaller function. So it is interesting to quote that, tortoise have ran faster than rabbit. It is not interesting to say that rabbit is running faster than tortoise, because that is trivially known. So same way, log of log n to belong to small o of log n is trivial, because we know that, theoretically we know that. But log n to belong to omega of log n is a very interesting result. This is one of the papers published in long back in mathematics. So if you see this quantum theory of quantum computing comes from, as the guy says, the field medalist says, it's a gift from mathematics, it's a gift from computer science to man. Many mathematicians have worked on this. Okay. So you see a lot of papers working on such kind of things. In fact, Indians are well known for this. Ramanujan's most of his effort is on solving this kind of theoretical things which are used nowadays to analyze the algorithm. Okay. And then I have given some interesting functions. So this, I don't know, because many of you are beginners. Many of you are mostly using the big O. I'll skip this. Okay. So there are other notations. You can go Google it, or you can refer to the journal paper I told. That summarizes all the 5 notations in detailed manner, which may help you to do that. Okay. So we have also given a geometric view of small o and big O and all that. Okay. So yes. So this is the paper, asymptotic notation, algebraic and geometric view, Ramanujan mass theory, and we have proved some of these results, some of these observations we have proved, which has helped us to analyze some algorithms which are non-polynomial time. And so when you have a non-polynomial time, we try to looking for better algorithms which can work for when the computing is huge. We need algorithm to implement it. Then we look for algorithms which can work with big O notations and theta notations and omega notations. Okay, and that is what this is all about. Okay. So, yeah. So any questions so far from any of you? If you have any questions, just ask me now. And in the meantime, I'll open the other side.
No, sir. No, sir. No, sir. You can proceed now.
No question from everyone is clear. Okay. So it's boring. Either you have not understood anything or it's boring. Right? No answer.
It's not boring, sir.
Okay.
But we need to do some more study on this theta and all.
Okay. Okay. That's fair enough. Yeah. Yeah, because this is very few people are working on this, but this is the kind of theory behind the quantum computing. Okay. So might help you sometime. Okay, so maybe I'll show one simple practical problem. Okay, which has become a product now. Okay, So we all know this, big data companies are nowadays huge. There are a huge number of funding coming from, especially your faculty members. If you are interested in writing a proposal, nowadays you can write a proposal in big data analytics. Okay. Theoretically, if you are not interested in writing in algorithm side, it's okay. But if you want, you can always write in this huge funding from the government side. Okay. There are many startup companies that come. Okay. From 2010, you can see that there are huge number of companies in a short span of time. I didn't write this 20. This data as of 2020. Okay. And many products have come out. Many publications also come out up to 2018. So if you see that there is a huge jump. 2011, there was nothing much on big data at all. 2011, up to 2011, people are not publishing. And most of these are engineers papers. It is not mathematics papers. These are all algorithms for solving, big data questions. Like there are various big data questions. No? Data is huge. Can you run it in a machine using Python or whatever, or in a cloud, and do the prediction and give that to us? Or in other way around, nowadays there are a lot of mobile packages available where one can predict, image processing, or one can predict whether it rains tomorrow or not. One can predict whether someone will clear an exam or not. There are a lot of predictions happening, right? Not only in horoscope, but also in mathematics and physics and computer science and all that. Recently I saw an app, in US, some students have done it. So the clip says that you have to just talk to the app for 1 or 2 days. The app will stay with you, and you need an Apple phone, Apple Watch to sync your fitness also to that. 2 days, the app will connect the data and says that whether you are fit for research or not, or you have to go to industry and work. So the app at the end tells undergraduate students to decide. Okay, so it studies the person, his behavior for 2 days. Good 2 days. So it's not like if he's sleeping. It's not weekend. 2 aggressive days of the sample, and it gives a prediction. So there are nowadays a lot of big data apps are coming up. Okay, these are some of them. Okay, so if you see that publications are more, you also see that big data companies across the globe is also more. Okay, this I have done some study for our university, so I'm sharing with you. And big data companies are also coming up in huge number nowadays across the globe, not only in India, everywhere. You see that many companies are coming up. This I'm saying in a particular year, this many companies have come up. Okay, India had 41 companies in 1 year. Okay, so that is it. So yeah. So this is another thing that you might have seen, AI Polyvision app. I don't know, do you have seen this app? Waymo is anyway, Google's, it is already a product now. 2016, Google introduced that, now it's a product. In US, there are cars where AI runs the car, right? So, without a human, machine runs the car, drives the car, and bring you safe. But there's another app called the AI Polyvision, especially for people who cannot see. So this app is like, if you take a photo, it will tell what is that in the photo. But especially for blind people, they have an app. So this helps you to do this. Nowadays in India, there is an app that comes for crops, especially I think in Maharashtra, someone has made an app where if you take a photo of the crop, it will tell you what the farmer should do. What is the next step for the farmer? He has to make some n number of pictures. The cloud will run in the cloud and give an output for it. So there are so many apps nowadays coming in AI to replace the human. So I'll take one simple, problem, and we say how, some people are making publication out of that. I thought this may be useful to you, some of you, how to write a publication in a simple task, okay, a simple problem. So this problem is taken from a website called the Kaggle. I don't know how many of you know Kaggle, Kaggle. It is here. You see the Kaggle, the categories of fishes to be classified, www.kaggle.com. You can note down this. This Kaggle.com is a website which shares lot of big data problems. Okay, so this problem is taken from Kaggle. So the data is that so it's something like this. When the people go to catch fishes, we know that tuna cannot be captured every time in the thing. We also have this mean Tadai column, right? In those days, you won't get fish at all, right? Like that. So in US, there is a time. In certain time, you cannot capture certain variety of fish. For example, tuna especially. Okay, right? So the project is given by a fishery, conservancy organization, government organization in US, where the problem is something like this. Okay, so these are the 6 types of fishes. Okay, which are to be processed and identified. In other words, so this kind of photos are given to you. These are the images taken in the boat. Okay, so the guys who catch fish are not educated anyway. So these guys are not. They will not be able to recognize the fish by looking at it. So they want a machine to recognize and tell what fish is being caught and which fish should be thrown away into the sea again. Okay, so this is a sample of images taken from the sample. If you see that, in the first image, the fish is hanging on the ship. Okay, on the side of the ship. In second one, the fish is very clearly visible, and fourth one of the fish is visible. Third one of the fish is visible. So these are the categories of these are the samples of images given by the fishery conservancy, organization. And the problem is something like this. You have to have an algorithm. So so if you look at it, how many images? Look at this back again. The data set is having about 4,000 images, 3,777 images, and in 8 folders. Okay, in other words, the 6 are the categories, therefore covering 6 folders. 7th is fish other than this. Okay, there may be other fish, right? And the 8th one is image without fish. Okay, so the folders are 8 folders. Okay, there are some photos where there is no fish at all. That is categorized there. And then this 6 category fishes are put in another 6 categories, another 6 folders. And the 8th folder is fish, other fishes other than these fishes. Okay, so the project is to make an algorithm, artificial intelligence algorithm, AI algorithm, in which if a random image comes, your algorithm should be able to compare with the database of this 3,777 images and then make a decision, the image classification problem. So if you see this, how people have gone about this. This is one problem that we also solved. We didn't publish, but I think we didn't publish, but we thought we'll just do this. Okay. So what you do is first you have to make these images. So 3,700 images to go into a RAM is not possible at all. Or if you put in a cloud, you have to pay huge money for the cloud because the images size will be around what? Until somewhere. I forgot, it was a huge size. Okay. Something like, images are color images, right? So the sizes are going to be at least, even if you put, say, let's say 500 MB or something, images are big, right? So we cannot use our RAM. Anyway, serially, you cannot do anything. Your laptop or your monitor may not have more than 16 GB or 32 GB. It's not going to work. So even if you go to cloud, you cannot do that. So what we have to do is, we have to do this is one of the problems in India, because we don't have good infrastructure in India, especially in colleges and universities. We don't have big cloud computing infrastructure or something like that. So we often depend on our laptops and our desktops, though they're reasonably okay. But this kind of problem, they don't work. That is the reason that India is not growing in AI. If you want AI products to come out, we should have a good infrastructure on computing, but that is not the case anyway. Even Central University is also not an exception. Even IIT is not an exception. I studied in IIT, I know that. Even IIT, we don't have big computing. If you compare to, in abroad, India, even the good institute doesn't have a big infrastructure, but IITs are better than us in some sense. So the only way is to compress the data. So only best way that we can do is we go to grayscale and then, do that. Okay. So this is a sample I just want to show you. Sample images. Not all the images are same size. So once you make it to grayscale, then your challenge is, your accuracy is going to be impacted because it is not going to give the desired accuracy, because you get blue. It's very difficult to distinguish a fish and a bottle because they both may look alike, because you have edge detection may be a problem and all that. So we know what are the things that comes on image processing. Now the algorithm is that machine has to do it on its own. That's the problem. So often machine get confused with grayscale images, but there's no other way. We have to do this. So what we play is we play with, play with the number of iterations. Okay. So we run, we run more number of times to do better. See, it's simple. Okay. You go to a class, you attend someone's lecture, you don't follow anything. What do? You just go to the book and read again. You understand a little bit. Or you go and sit in the lecture again. So you do repeatedly n number of times or 4 times, 5 times, your understanding become better, right? Same way, you have to let the machine to do that. Machine to run again and again, study again and again. Okay. So in that way, that's what we are exploiting. We are using human learning to model the machine learning. And so grayscale images are compromised in that way, but we are able to achieve a better accuracy. Okay. So, and we also do the resizing of the images to uniformly to 256 by 256 because some images are bigger, as you see here. Original image is 1518 by 854, but we resize to 250 by 255 because again compression happens here, loss of data. But again, we have to do what you have to do is like we have to redo the things. Something like we are not able to buy a good book. We are having a Xerox of a book, but the printing is not good. What do? You look into that multiple times and try to guess what is there and you study that, right? Like something like that. So you have to let the machine to not to assume something.
Exactly.
Machine to look at it again and again and do this. Yeah. Any question? Any question? Okay. Okay, so something like that. Okay. So anyway, I will not get into this theoretical part of convolutional neural network. You all know that, or some of you may not know. You just go to the theory, go read. There are the algorithm itself is like it's all matrix theory anyway. At the end, to do with the eigenvalues, so you have to choose the images properly. When you do the when you do the compression, you have to be careful. One thing that I found is the eigenvalue of the matrix is very important for the images. So image is a matrix, right? You all know that 256 by 256 matrix. So what one can do is always is first to go use MATLAB or something or Python or something and find all the eigenvalues of them. First see whether they are non-singular or not. Okay, this is some of the things that really work for me. I'm telling you. Okay, and in that case, our algorithm is better than a smarter algorithm, other algorithms. Okay, so these are some of the things you take that. Okay, in other words, the compression should be in such a way that the matrix, the resulting matrix of the image should be a non-singular matrix. Okay, that means your rows are not dependent, right? That means in the pixel rows are not linear multiple of other. In that way, machine won't get confused much. Okay, so that is simple logic. And then eigenvalues. Okay, so in some sense, if the eigenvalues are better behaving in a small neighborhood or something, then the matrix is easy to solve, right? So you have studied numerical analysis. Someone who has studied numerical analysis, the Gauss elimination method, right? If you have a matrix which can be reduced to diagonal matrix, then you say that the matrix that problem can be solved, the linear equation can be solved easily, right? The same way, the same logic will work here. Okay. So if you have a matrix after reduction, if a matrix happen to have a well-behaving, entries after row reduction, if it has well-behaving, column matrix or above column matrix or below column matrix, then such compressions are working fine. But I don't know why it is so. Theoretically, I don't know, but such matrices are computing. One reason I did was because computing can be faster for that. Meaning I don't need to confuse the machine. So machine can give a output faster. So put it theoretically, for engineers, you also study numerical analysis. When you have a matrix or when you have a linear system to solve, you go into matrix. Then you do row reduced echelon matrix and all that. So if your reduced matrix is a diagonal matrix, then you don't need a computer to solve it now. You can easily say what is the value of the solution, right? Just you have to solve by eyes, you can say that, right? Because diagonal matrix times the variable is equal to constant. You can easily solve it by mind, right? Same way. So if your matrix happens to be a diagonally reducible matrix, in other words, the row reduction and column reduction can lead to a diagonal, then it is easy for the machine to solve it because it's also easy for the human to solve it. So it's also easy for the machine to solve it. Therefore, theoretically, what we say is when you compress the images, when you resize the images, careful with that. The resulting image is a matrix for the machine. After reduction, the matrix should be a well-behaving matrix. In other words, if we do row operation, column operation, it should be diagonally dominant. It should be a diagonal matrix. Okay. If it is at least diagonally dominant, it is better. Okay. So I'll skip this anyway. it's already, boring you with so many theories. So I'll not worry about this. So you all know what is false positive and false negative in machine learning algorithm. For mathematics people, I'll just say that. So what is false positive is something like, suppose let us say you want to predict something. Okay. Something is falsely predicted as positive. Something falsely predicted as negative. Okay. So we often make a confusion matrix for the prediction. True, false, but false and true, which is another way around. So I'll show you the confusion matrix and then, okay. So these are the misses in the, so if you look at this matrix here, so as I said, this is a 10 by 10 matrix because this problem has 10 folders, right? So now if you see the diagonal matrix, first entry says 328. That means 328 images are correctly identified in the folder. That means 328 images having the particular class of fish is identified to saying that machine has identified that it is that particular class of fishes in the image. Okay. If you see the 6 below that, it's a mistake. It's an error from the machine. Okay. It is an error. What is the error? The error is like it is falsely predicted as 1, but it's supposed to be in 2. Okay. So we call this as confusion matrix because this is how machine is confused. It says how machine is confused in its learning. Okay. If your diagonal off, if your off diagonal at this is 0, that is the best algorithm. That means every prediction is correct. Okay. But that is very rare to occur. Or that such problems are not hard problems. Okay. But this is the one. See, in this algorithm, when you use one convolution layer, we take this. So when you do for 2 convolution layer for the algorithm is slightly getting better. Accuracy is improving by 1%. Okay. So we have got 92% accuracy. In other words, if you give a sample of 100 images, the algorithm is able to classify 92 images correctly and about 8 images wrong. That's what we mean by 92% accuracy. Okay. And this is how the confusion matrix is drawn. So when you use 3 convolution layer, it has given 45% accuracy. That means machine got confused really a lot. In other words, what is the analogy of this? You read a book once, you have got a score of 92%. You have an exam, you got a score of 92%. Okay. Now you read the book 2 times and you appeared for the exam, you got 93%. You read the book 3 times and appeared in the exam, now you got only 45% marks. What does it mean? It has confused you more. Okay. So this also happens in machine learning. When you do convolute again and again, you should really get confused and then do this. You can try this with the ChatGPT. Okay. You just go and ask ChatGPT something. And you ask ChatGPT, just ask a hard question. Okay. Don't ask a trivial question. Just ask a hard question. And then ask ChatGPT, are you sure? Okay. Can you redo this, study this and give again? Okay. That's a very good chance that ChatGPT will give an entirely wrong answer to you, entirely different answer to you. Okay. So there are a lot of problems for that. Okay. If you choose a problem correctly, you can always decide that. So what does it mean? That means algorithm got confused, with your question. Because the algorithm is iteratively asking you and giving you an answer. Even though the answer is correct, you are asking, are you sure? Okay. Then the algorithm take it as like the user has given a negation and therefore he has to go through the data again. After going through the data again, the machine is confused. Okay, the second convolution has created the error. So this has happened here. So what we did was we again went back to our resizing strategy, and then that's how we identified that having a better eigenvalue is a good question. Okay. So I don't have the slide here, I think. I don't have the slide here. So what we did was, this slide has only 93% accuracy. So what we have done is we have taken resizing strategy again, and we did resizing. We allowed a different algorithm to do resizing in such a way that the resulting matrix is not only diagonal dominant, it is also having a spectrum of eigenvalues to be in a radius. So you all know spectrum, right? You have studied spectrum of eigenvalues. No? You have a spectral radius, right? So spectral radius are bounded near 1. Okay, so if you do that, we are able to achieve. We achieved around 98% accuracy in this. Okay, so this is the scalability. What is happening is when your sample is increasing from 1000 to 3777, or maybe beyond that, okay, you face, issues of this kind. Okay. We also developed an app on, identifying COVID from X-ray images. In the app is like the app that's on cloud. Okay. And maybe I'll share the app after the lecture. The app is not yet approved in Android. We're just in the approval stage. Okay. So the app sits in the cloud and then takes the data from you and goes to the cloud, which has about 10,000 images, and then give the output for you. And the accuracy is 99%, 98 point something, 98 close to 99%. Okay. So 98.9% of the. So what I mean to say here is a summary. So for example, you just go to Python. For convolution, there is a package. So if you understand the problem, you can always do the first step. Okay. So you may get around 50% accuracy. Okay, that everyone can do. Even a +2 kid can do that. Now the question is how to improve the accuracy. Now 3,700 images, a big image. Okay, it's a big data. Reasonably big data because this cannot sit in your machine. Okay, your RAM is much smaller than this size. It's difficult. Even after compression, it won't sit in your images. But suppose if 3,700 is not enough, for a prediction. Suppose the data is like 1 lakh images. So these are all, you understand now the N has become larger now. Okay. So when N has become larger now, we saw na Thiruvalur's quote na Pilive Sagadu Machinum Padam. There's small error. When N is smaller, it is okay. But when N is bigger and bigger, it becomes. So in computer science, they call it as Archimedean problem. That means a small error can lead to a big error. Okay. So in Tamil, there is another saying that that is because of this. Because the crime also will increase. So we will be caught one day. That's what the theory of quantum computing. Okay. So what you have to do is, first stage, everyone can do that. Go to Python, implement the problem. Yeah, there are little headache in this, how to take the data to the machine, all that is there. But if you look at YouTube videos, it's there. But what I talk today is about taking your accuracy from 93 to 98%. How do you do that? Or 93 to 95%, 98, 96%, or even 45, 50 to 90%. Okay. This is done by looking at where the errors are coming from. Where are the iterations? Where are the even small errors? You have to focus on that. Okay. Because when N is huge, small error will lead to big error. Feather of a peacock is light, but if N number of peacocks, feather can break the wing. So it can break the algorithm. That is the theory behind it. So that identification leads to look at the matrix. That means look at the images. The input has an issue. Now how to make the input better is, but on contra positive of this, if you look at US, the same data, it's an international website. Okay. So when you solve it, you go and post your output in the website and they give you a rank. Okay. So we got we were the last 10 or something like that. Let's say 1,500 people submitted all over the world. Our rank was 1,490 or something like that. Okay. So there were few more people below us. But if you see the input, if you see the postings from US and China and Europe, these guys are very good machines. Okay. So they don't need to compress the image at all. They use the same images to run that. So US have, if you go to universities in US, they have 1 lakh cluster. Okay. But none of the IITs have 1,000 cluster now. That means they have 10 to the power 6 machines together in one room. We don't have even 1,000 images. IIT Madras doesn't have 1,000, I think they have, now only they added 1,000, I think. Recently they added, 5 years before. Until then, even now they have only 1,000 node in a parallel computer. Okay. So computing infrastructure of India is very, very bad. So keep that in mind. Why I'm emphasizing that is, you can't compete with an American doing computing on such data. So our strength is complexity, analysis of algorithm. What we can do is, with this resource, how to do that, our question will come. This kind of, theoretically, playing with to improve the accuracy is the better choice. Okay. So this is what all about I have. So I'll keep the next 5 to 15 minutes for discussion. If you have any question, please ask me. I hope you were able to follow me. I don't know whether it is true or not, because online is always a difficult. But advanced uses we can always follow in online.
Yes, sir. I have one question in image processing.
Yeah.
In image processing, we usually convert an RGB image to grayscale. Yes, sir? Is it possible to process an RGB image without converting it to grayscale?
Yeah. So it's simple. Okay. So now if you see, okay. Okay. So this is the image. Okay. You see a matrix.
Yes, sir.
So n by n, k by k matrix. It's an image.
Yes.
Okay. So it's a grayscale. Therefore, every entry is going to be one score because the grayscale, right? Grayscale will vary from 0 to 255, right? So it's
Yes,
going to
sir.
be a number. So every entry is going to be a number. If you have RGB, then you have a combination of red, green, and blue. That's all, right?
Yes, sir.
The only problem is your data will increase. Okay, your size will increase. So the question is, theoretically, there is one question that image processing, RGB has not much role. RGB is only for graphic. Okay, to put the output,
Yeah.
to present the result, you need to worry about RGB.
Yes,
Because
sir.
at the-
In our output, it is a grayscale. How to convert it as a RGB image?
Say it again.
Sir, basically, we are processing in grayscale image. The output is in grayscale. How to convert into RGB image?
Okay. No. Okay, so yeah, fine. Okay, so the question is, I have a color image. For computing, I convert it to grayscale. Now I
Yes,
got
sir.
the output. Now I get, how do I get back the packages? Don't worry about that. OpenGV will
Yes.
do. That will give you because it's simple. Okay, what it does is, the image, see at the end, what is an image? See, for example, if there is a fish in the image, if you see that. Okay, I understand what is the so take this, okay. If there is a fish in the image, right? The boundary of the fish is converted into grayscale, that's all. Okay. But you have the vector, right? You have the vector ready with you, right? The conversion is happening from
Yes,
is a function from R3 to R. And the function is a linear function, okay, isomorphism. That means you can always invert back. Yeah, suppose I take a pixel of an image, which is RGB. Now I have three values, R, G, and B, right? Now I transform them into grayscale by a function. The function is a one-on-one function. That means inverse exists for that.
Yes, sir.
Okay. It is not like sambar. You mix dal and vegetables and something, three things together, you make sambar, but you cannot take back the vegetable from there, right? Once sambar is made, you cannot take it back because making sambar is not a one-on-one function. Okay, but this mapping is a one-on-one function. We often take linearly. Either we add all of them and take confluence over 255, or many algorithms are there. What I'm saying is the transformation of red, green, blue to grayscale is a linear and one-on-one function. So the machine itself will do that. You don't need to do that. It will be done. Understand? You understand?
Yes, sir. Yes, sir.
So it's
Thank you, sir.
calculated. The only challenge is how to find the grayscale image. That is challenge because machine is processing only the grayscale images, not the color images. That's the problem.
Okay, sir.
As I said, we are doing it because we are in India. That is the problem. In India, we have not huge computing infrastructure, right? So we have to do all this. Otherwise, if you go to US and all, these guys run with the color images because they have a luxury of huge machines and they can run on that.
Okay, okay. Thank you, sir.
Yeah, thank you. Yeah, that's a good question. At least one or two questions. I'll be happy that someone watched. You also tired after your college, you know? You come from your college and then you have to attend this refresher course. I understand that. Any other question? Or you can also ask not from here, anything general for you. You want to ask how to do computing, what is the nature of this, you can ask me. I also worked in the industry for about 5 years. Okay. So I have this computing infrastructure from industry perspective as well. So you can ask any general question if you have.
Sir, how this image classification problem can be solved by using quantum computers, sir?
See, it's very simple. Okay. If the data is going to be huge now, okay. If the data is going to be huge, okay, then you are going to look at, there's going to be intensive computing involved in that, right? That is one kind of quantum computing. Okay. You understand what I'm saying?
Yes, sir.
Right? so not really huge. Okay, see, for example, even the images may be 3777, but it's not possible to handle it in your serial machine, right? It needs some intensive, detailing of all the images and then look at it, right? So there are different strategies, not only only with eigenvalues. There are many ways people have done this. Okay, some people have used even Turing machines some Turing machine based algorithm to look into that and all that. So these are all very intensive computing. Okay, so which are one kind of quantum computing.
Okay, sir. Okay. Thank you, sir.
These are only words. Okay, quantum computing is just a word, But when you go to when you generalize it, industry, what they're looking for is machine is powerful now. Problem is also very large, but most of the algorithms are giving output in 2 days time and 3 days time. Now, can you improve the algorithm to give output in half of the time, or make the algorithm better? That is the simplest question that industry is looking for. Okay, so if you answer this, there's enough. Yeah.
Thank you, Dr. Ramesh, for your valuable session. With that, we are concluding the day 2. And tomorrow we are having Dr. Venkatesan as well as Dr. Venkata Subramanian. And I'll see you all at 6 o'clock tomorrow. Thank you very much.
Yeah, thank you. I also thank the organizer for the opportunity to give a talk here. And also all of you for patiently listening to me. Thank you. All the very best.
You're welcome, sir. Thank you very much.
Thank you.